I want to talk today about nucleophilic acyl substitution, and in order to have that discussion, we need to talk about carboxylic acid derivatives. So here's the generic structure of a carboxylic acid, and in terms of the derivatives we're going to talk about today, we'll talk about acid halides, which include acid chlorides and acid bromides. We'll talk about acid anhydrides, which have this general structure. We'll talk about esters, which have the OH of the carboxylic acid replaced with a OR2 and ether type group on the ester. The last carboxylic acid derivative we're going to talk about are amides, which have this general form where the OR or the O or the Cl and the other derivatives have been replaced with an amine group. So let's look at how these react in the nucleophilic acyl substitution reaction. In the nucleophilic acyl substitution reaction, we have some carboxylic acid derivative, and we have a nucleophile. The nucleophile attacks the carbonyl carbon. The electrons move up from the double bond, move up onto the oxygen, and we get a tetrahedral intermediate that looks like this. The next thing that's going to happen is the electrons on the oxygen are going to come back down, and one of these two groups is going to leave. Either the X is going to leave or the nucleophile has to leave. And something has to leave because we're making a new double bond here, and we can only have 4 bonds on carbon. So if the X group leaves, so the electrons on the oxygen come down, my X leaves, I get this product right here where the nucleophile has replaced the X. Since this is a nucleophile and it's substituted for X on my acyl group, this is the nucleophilic acyl substitution product. On the other hand, maybe the electrons on the oxygen come down and my nucleophile leaves, as shown here. In this case, I get back exactly what I started with. In other words, I get no reaction. So what determines which of these two groups leave, whether the X group leaves or the nucleophile that just came in leaves? It all depends on which is a better leaving group. Remember what you've talked about in past classes, the relationship for identifying whether something is a good leaving group or a bad leaving group is its base strength. Something that is a weak base is a good leaving group. So if we compare the base strength of our two nucleophiles, and X is a weaker base, then it's going to be a better leaving group, and we get the nucleophilic acyl substitution product. On the other hand, if the nucleophile is a weaker base than X, it's going to be the better leaving group, and we get our reactant right back. So let's look at our different carboxylic acid derivatives and look at the leaving groups that each of them contain. And the leaving group is going to be the thing attached to the carbonyl. And I'm going to arrange them in order of basicity. I'm going to put the least basic at the top and the most basic at the bottom. So if we start with the most basic at the top, the most basic is definitely going to be the Cl or the Br from the acid chloride or the acid bromide. Chloride or bromide are the anions of strong acids, so they're weak bases. Next, we're going to look at the leaving group of the acid anhydride, because that is the next weakest base. And that has a somewhat unusual structure compared to the other ones. It looks like this. It's essentially the anion of a carboxylic acid. Next is going to be the leaving group for an ester. It's going to be an alkoxide group. And this alkoxide group is definitely a stronger base than the carboxylate group. Following that, we have the leaving group from the amide, which is the nitrogen-containing moiety over here. So this nitrogen with 2 R groups on it and a negative charge is weaker than the alkoxide group as a leaving group. Down the bottom of our chart, actually, we have the leaving group of the carboxylic acid, and that actually requires a little bit of an explanation. So I'm going to put the leaving group down there, and then we're going to talk about it for a minute. So OH minus from a carboxylic acid. And if you remember your leaving group trends from previous classes, you might remember that OH minus should be really similar in strength to the RO minus, and it should be a weaker base than the nitrogen containing base. So why do I have it lower? Because something really sort of interesting happens with a carboxylic acid because we don't really have OH minus present. What happens is, since this is a carboxylic acid, it acts as an acid and loses a hydrogen. So really, most of the time we have this carboxylic anion hanging around rather than the protonated carboxylic acid. So we really have this. So what our leaving group really is for a carboxylic acid is not the OH. It really is O minus 2, which is why we have it at the bottom of our chart, because O minus 2 is like the worst possible leaving group you could almost ever imagine. And I want to remind you that leaving a group ability goes in the opposite direction. So the poor leaving groups will be down here, the strong bases. The weak leaving groups will be up here with the weak bases. So how are we going to use all of this information to understand what's going on in the reactions we see? Well, there's one general rule you want to follow. You can convert from something with a good leaving group to a poor leaving group, but you can't go in the other direction. In other words, you can go down the table. You can go from something higher up on this table to something lower on the table. So we can go from an acid chloride to an amide, or an acid chloride to an ester. But I can't go from an ester to a carboxylic acid anhydride and so on. So let's look at a couple of examples. So if I start with benzoyl bromide and I react this with methoxide, my leaving group is bromine. My nucleophile is CH3O minus. The bromine is higher up on the table than the RO minus. Since the Br minus is a weaker base than my RO minus, it's a better leaving group, and this reaction will work. In fact, reactions like this are fairly common ways of making esters. A lot of times you use the acid chloride, but you can also use the acid bromide as well. Let's look at another example. I have the same nucleophile this time, CH3O minus, but this time my leaving group is different. It's CH3CH3N minus, so it's down here. My leaving group is lower on the table than my incoming nucleophile. My leaving group is not as good a leaving group as my nucleophile is. This is higher up on the table. It's a weaker base, and it will be the better leaving group. This reaction, where my leaving group, my nucleophile is here, my leaving group is here, this will not happen. Compare this to the first reaction. My leaving group was higher up on my table. It was a weaker base. The reaction can happen. Your leaving group has to be the weaker base. That's not the case in this second reaction. This reaction will not happen. So what if you did want to accomplish this? What if you wanted to convert the amide into an ester? Does this mean that there's no way you could do it? You can do it, but it takes several steps. So let's look at what you have to do if you need to go from something that has the leaving group that's not going to leave because it's not the weakest base. The first thing you have to do is you have to hydrolyze the amide to the carboxylic acid. So you can do this with acid or base. I've used base here. So basically what we're doing is we're going all the way down to the bottom of our table. And this will work because OH minus is going to get rid of my N, is a hydrolysis reaction. In other words, the N-containing group is a better leaving group than my OH minus, because remember, it's really in the form of O2 minus. And we will get my carboxylic acid. That's the first step. The next step is to use thionyl chloride, SOCl2, to convert my carboxylic acid to my acid chloride. So see what I've done? I've come from all the way down the bottom of my table all the way back up to the top. This gives me something that has a really good leaving group in it. Now I can convert that to anything on the table below it that has the weaker leaving groups. So I can go to my ester now. And if I react methoxide, I will get my ester. So when I'm trying to go to something that has a leaving group that's higher up on my table, that's a weaker base, that's a better leaving group, I have to use this 1, 2, 3-step process. However, if I was going down the table from something that has a strong leaving group to a weak leaving group, I could go directly in one step, as we saw before.